So yesterday, we were working on vertical circular motion. We looked at 3 places in the vertical circle. We looked at the top on the inside, which is what this question is about. We just did a question on the quiz that was dealing with the top on the outside, and we also dealt with the bottom of the loop on the inside. Okay? The challenge with these locations is simply to determine what are the forces that are present and which way are they acting so that I can use them all, okay, in this formula, which applies no matter which position in the circle I am dealing with. Okay, so if I'm dealing with this position here, normal force acts out until it's what?
On the inside.
Nope. Till Fn is what? Eventually, if I go fast enough,
0.
Fn becomes 0, right? Because that's where we can achieve that feeling of apparent weightlessness that we talked about. We watched all those videos about yesterday. Okay, and then gravity is obviously always present, acting into the circle. Okay, at the bottom of the circle, gravity acts out of the circle, and normal force acts in. How do you feel at this point in the circle? Heavy. Yeah, you're either exactly the same weight, which would only happen if you weren't moving, okay, or you are heavier. So at the bottom, you are always going to feel heavier. Your apparent weight is always going to be greater than your actual weight, because not only is gravity trying to pull you out, your inertia is trying to pull you out, okay, well, not really pull you out, you're just trying to go that way, and the cart has to push on the track, and the track has to push harder, okay, making you feel heavier. Now, what's the weird thing about this position that neither of these positions has? Okay,
Pushing out.
it could, yes, its inertia wants it to push outwards, but what is there that the other two don't have?
It doesn't have a force pushing outward.
Okay, it doesn't have a force pushing outwards. I walked into that one, you're totally right. I was thinking of something else. There's this thing that's present. If I don't have it, I'm not going to get through the circle. A minimum velocity or minimum speed. I can't fall out of the circle here. I can't fall out of the circle here. I can go as slow as I want in either of these 2 positions and I'll be okay. But in this position, if I don't go fast enough, I fall into the circle. Okay, so that is the only one where there is a minimum speed. And, Deacon, you were right, it is also the only one where there is no force acting out. Okay, there's either just gravity, or there's gravity and normal force both pushing in. If I'm going just fast enough to stay in the circle, do I have any normal force? I don't, because I'm not pushing on the track, and the track isn't pushing back. Okay, so in this particular question here, okay, they want us to figure out what the minimum speed of this particular loop is. Okay, so they're telling us that it's a 700 kilogram roller coaster, and they're wanting us to calculate the minimum speed for a diameter of 50 meters. So, if I go back to this idea here, Fc equals forces in minus forces out, and then I go, all right, I've got gravity. Do I have anything else? No. At the minimum speed, only gravity acts as a centripetal force. Okay, so there are no forces out. And the only force in is gravity, so we're back to this. Fc equals Fg. You are essentially a projectile. You would feel weightless at this point. Okay? Okay, did they need to tell us the mass of the roller coaster? Nope, it's going to cancel anyway. If it was going faster than the minimum speed, would the mass matter? Yes, it would. Okay. All right. So I'm going to cancel the masses. I'm going to multiply both sides by r. I'm going to square root and calculate the minimum speed for this particular circle. Why do you use 25? It's the the radius. They told me the diameter. It's a dirty trick and they played it. Okay, so. Alright, so we're looking at a minimum speed of 16, oh, we've got three significant digits, 15.7 meters per second. Okay. Everybody all right with that? Okay, I would like you guys to try those two, please. Okay, so we're looking for minimum speed, so it's the same calculation we just did with the roller coaster, okay, except this time we're being told that it's a toy car and that it's a radius of 15 centimeters, which I'm going to convert to meters right away, okay. If it's talking about minimum speed, it automatically is telling me I'm dealing with that position, because as we said a few minutes ago, that's the only position that has a minimum speed, okay. So if it's traveling at the minimum speed, only gravity is acting towards the center. There are no forces out. Fc equals forces in minus forces out. Nothing. This is it. Okay, so that's going to be mv squared over r equals m times g. I'm solving for r, so I'm going to bring r over to this side. I'm going to divide both sides by m times g, which is going to cancel the m's. Okay, and so I'm going to have that v squared over g equals r. And when I put in those calculations, oh sorry, I'm looking for the speed. Take it out. V is going to equal the square root of GER, as we said before. Okay, so 9.81 times the radius, which is 0.15 meters. Okay, so when we plug that in, we should get our 1.21 meters per second. So on number 2, now we're looking for radius. Okay, they're telling us that this is the speed that would be required to go around safely. In other words, that is the minimum speed. All right, so again, we're talking about the top on the inside of this vertical loop. Okay, and so we want to go mv squared over r equals m times g, because that's forces in minus forces out. Okay, so we're looking for r, so we're going to multiply both sides by r, which is the manipulation I was doing before. Okay, and I got ahead of myself there. So we're going to have 20 squared divided by 9.81, and that'll give us our radius, which should come out to 40.8 meters. Okay, I want you guys to try this one. So now we're dealing with the bottom of the circle. And now it's a bucket on a rope. So it's not normal force. We're switching normal force for... Yeah, no, that's actually not, I actually wasn't pointing at you. But yes, you can. So instead of normal force, because it's on a rope, what does a rope provide? Tension. Okay, so whenever you have something on a rope, tension substitutes for normal force. Okay, so we're dealing with the bottom of the vertical circle now. They want to know the tension in that rope. Okay, and as I said, that's going to act as normal force instead. So, okay, here's our situation. They've got the forces identified on there for you. Okay, they've got the radius there. You know the speed. Okay, we're just looking for that tension in the rope. Give you a few minutes on that one. Forces in minus forces out. Okay, so we're at the bottom of the vertical circle this time. Okay, this formula, as we said before, still applies. Forces in minus forces out. In this case, that's going to be Fc equals tension, because it's acting in, minus gravity. Okay, those are our forces. We're looking for the tension, so we got to move the force of gravity over to the other side. Now, since I'm subtracting gravity, if I want to move to the other side, I've got to add it. Does that make the tension pretty big? Did we say you always feel heaviest at the bottom? Yeah, that's because you're going to add the force of gravity to that centripetal force to get the force you actually have to pull with. Okay, so we're going to have Fc plus Fg equals the tension. Okay, so that's going to be mv squared over r plus m times g, which in this case is going to be 1.5 times 3 squared, because they told us the speed, okay, divided by the radius, 0.75, plus 1.5 times 9.81. That's going to give us our tension, okay, so that's going to be 1.5 times 9 divided by 0.75, and then we're going to add that to 1.5 times 9.1. Okay, so we're looking at a tension of 33 newtons. Okay, everybody follow what I did there?
Yeah.
Right, just forces in minus forces out. Okay, give these ones a try, but don't do number 2. Okay, so we're looking for the tension in the rope in position A. Now, there is a problem with the way this question is set up. They're saying that the speed at the bottom of the circle is 3 meters per second. And now they're saying, using the information, determine the tension in the rope in position A. We have to assume the speed is 3. Is it? It would be slower than that, would it not? It wouldn't be 0. But it would be slower than 3 meters per second because we know the fastest point is the bottom. So they're just saying, use the same information, but now imagine that the speed at the top is 3. That would mean the bottom would be faster than that. Okay, they're just saying try it for number 3. Okay. Actually, you know what? Don't do number 1. I don't like how that's set up. Try number 3. Just do number 3.
Good deal. That's what we do it for you.
Okay, so for question number 3, they tell us the mass. Right, so we got 0.98 kilograms. Right, we know it's a 4.4 meter rope, so that's the radius. Okay, and it's spun in a vertical circle. The tension in the rope and the rock is at the top of the swing is 79 newtons down. All right, so we're dealing with this point here. Okay, so that's going to mean we got gravity, but they also tell us that there is tension. Both forces are there, and they both act which way? Down, which is from the circle in, okay, into the circle. All right, so if we're setting this up, Fc equals forces in, that would be gravity and tension, minus the forces out. There aren't any. Okay, so that's my formula. That's forces in minus forces out. There are only forces in, and I would add them together because they're both in. So I'm looking for, in this one, the speed of the rock. So I'm going to go mv squared over r equals m times g plus t, because they gave me what t was. Okay. All right, so I'm trying to get v by itself, so I'm going to multiply both sides by r. I'm going to bracket that because it needs to be done first. Okay, multiplied by r, and then I'm going to divide both sides by m, and then I will have to square root that to get v. That's probably the trickiest manipulation you're going to come up against, okay, in terms of vertical circles. Okay, so v is going to equal, right, the square root of 0.98 times 9.81 plus 79, and then multiplied by the radius, 0.4, divided by 0.98. Okay, so plug all that in, so we got 0.98 times 9.81 plus 79 times 0.4 divided by 0.98 square root. All right, 6 meters per second. 2 significant digits, 6.0 meters per second. Okay. Everybody all right with that one? So tricky manipulation. If you didn't bracket the mg plus t and you just typed the whole top in, you wouldn't have got the same answer because it would multiply t by r and then added that to mg, which is much different than the way we did it. Okay. All right, questions on number 3? give you about a 4-minute break here, and then we'll move on to the next type of thing. Okay, so if I'm dealing with the bottom of the loop, and the force that I feel is this force, as you guys just said, the force I feel is normal force, okay? Force of gravity is acting out, okay? And it's telling me that Fc is the forces in, that would be normal force, minus the forces out, and then they're telling me that Fn is 2 times heavier than normal. How do I calculate what I normally weigh? Mass times gravity. So would this calculate 2 times what I normally weigh? Yes, it would. Okay, so I've got Fc equals 2 mg minus mg. What's 2 mg minus mg? Mg. Okay, so this is more of an algebra trick than anything else. Okay, so I'm going to have mv squared over r equals forces in 2 mg minus forces out mg, and I'm going to be left with mg. What happens to the m's? Cancel. Okay, and then I got to multiply both sides by r, and then I got a square root. How many times has the final formula been the square root of GER? A lot. Like, honestly, if you were totally lost on a test and had no idea what to do for a vertical circular motion question, write that. There's probably a 25 to 30% chance it's right. I mean, it comes up that often. Right? I'm not saying that that's like a strategy for success. I'm saying if you had no other option and were completely lost. Okay? So when I plug in my numbers then, B is going to be the square root of, what was our radius? 35. So 35 times 9.81. Okay, so that roller coaster's got to be moving at, do we have only 2 sigmas? We did, so 19 meters per second. Okay, so it's not a lot of like, again, tricky math. Like, that's just algebra. It's the understanding part. It's understanding that if I feel 2 times heavier than normal, that means the force I feel is 2 mg. Okay, or 3 mg, or whatever it is they tell me how many times heavier than normal I feel. Okay, everybody all right with that? What if they told me I'm experiencing 4 G's? It'd be 4 times my weight, because G force is a factor. It's just saying this many times heavier than normal. So if it's 4 G's, it's 4 mg. Okay, if it's 10 G's, it's 10 mg. It's just one of those things that's going to come up. The way you calculate G force, which is a terrible name for it, because it's not a force at all, okay, is you take your apparent weight and you divide it by your actual weight. How heavy do you feel divided by how heavy you are tells you how many G's you are pulling. Okay, G force is not an actual force, it's a factor. Okay, it tells you you feel this many times heavier than normal.
In a plane, does it work the same, or would you also kind of feel like some weight from the plane as well? I don't really know how to explain it, but I feel like I remember searching it up, and they said that like when you're in a plane, you're pulling more G's than like if it's just your weight. So the weight of the plane also affect how many G's that you're pulling.
No.
So it'd still just be your mass.
You don't feel the plane. You only feel you. The plane feels the plane.
Okay.
So if it's pulling out of a dive, the plane's apparent weight is going to be the same number of times greater than as yours.
Okay.
Okay. So if you're pulling 6 G's, so is the plane.
Okay.
It just doesn't. You don't feel the weight of the plane.
Oh, okay. No, I just didn't understand how that worked.
Yeah. Does that make sense?
Yeah.
If you felt the weight of the plane, you'd get crushed.
Yeah.
It hurt. Okay, try that one. Looking for the apparent weight of a 75 kilogram person as they go over the top of a 150 meter circle. That's the radius. Okay, 150 meters at 22 meters per second. So you're going over the top. Outside or inside? Outside. Going over the top. Under the top would be on the inside. Okay, so for this one here, okay, we're looking for the apparent weight as they go over the top of this circle. Okay, so we're looking for Fn, which is the force acting out, Fg is the force acting in, right? We know their mass and we know the radius. So mass is 75, okay? Radius is 150 and the speed is 22 meters per second. All right, so we're going to have that Fc equals the forces in, gravity, minus the forces out, normal force, okay? And I'm being asked to calculate the normal force, so I'm going to swap it for Fc by adding it and then subtracting Fc. So I'll have Fn equals Fg minus Fc, which will be 75 times 9.81, that'll be my force of gravity, minus 75 times 22 squared divided by 150. Should this be lighter or heavier than their actual weight? Lighter. Yeah. Okay, so 75 times 9.81, okay, minus 75 times 22 squared divided by 150. All right, so 493.75 newtons. We only have two significant digits, so 4.9 times 10 to the 2 newtons. Okay, would be their apparent weight, and that would be directed upwards. Okay. Everybody all right with that one? Okay. Tomorrow, okay, we'll kind of work a little bit on some circular motion stuff, like vertical circular motion stuff, and then see how that goes. I may give you your circular motion assignment near the second half to end of class tomorrow, or if we're going a little slow, we'll just have Thursday to work on it instead. Okay, so we'll kind of see how that goes, but this is basically wrapping up first half, unit 3. So I'll be letting you know your exam date probably by Thursday. You get an idea. It's a short unit, guys.
Do we have another